Okay, let's look at this last problem set dealing with fluids. This is set number 29, and these are problems in chapter 10, 13, 17, and 18. Let's start with problem 13. We find that we have two objects. We have a green object and a yellow object. And these objects we are told the mass and the volume, and they both have the same mass. That mass is 600 grams. But they have very different volumes by a factor of 2. The green object has a volume of 800 centimeters cubed, and the yellow object has a volume of only 400 centimeters cubed. Now we can also just really quickly calculate their density. Remember the density is just the mass divided by the volume. And so here, if I take 600 and divide by 800, I get a density of 0.75 grams per cc. And here, if I take 600 and divide by 400, I get a density of 1.5 grams per cc. So that's going to tell us something about what these two objects will do in water. If I put them in a lake of fresh water, where the density of that water is 1, the green object is going to float at the top. Indeed, it will float with 75% submerged and 25% above. I know that because it's got a density that is 75% that of water. This will be the green object. Now, the yellow object is going to sink to the bottom. Okay? Because it has a density that's bigger than the density of water. Now, we're asked in this problem in part B to find the buoyant force exerted on each of these objects if they're fully submerged. Now, folks, I got to tell you, that's not the way I wrote the problem. And that's why the solution key looks a little bit wrong. The solution key was right when I wrote the problem, and then my co-author changed the problem. What I originally wrote was you put these things in the lake, you let them go, you wait a while, and then after a little while, what's the buoyant force? Well, in that case, the yellow object's down here, and the green object's up here. Well, in that case, in that problem, the buoyant force on the green object would be the weight of the green object, right? Because if I draw a free body diagram for that green object, there's just the weight force down and the buoyant force up. And the weight force is going to be the mass, which is 0.6 kilograms, times 10 newtons for each kilogram. Well, that's going to be 6 newtons. And that means the buoyant force would be 6 newtons. Okay? Now, if I were to work this problem the way the book has it written, then I would somehow have to submerge this block and that means I'm going to have some sort of hand holding it under. Well, in that case, the buoyant force is going to be equal to the weight of the fluid displaced. So I imagine a block of water that's the same size and shape as my green object. Well, I know that the green object is taking up a space, a total space of 800 centimeters cubed. Well, how much would that weigh? Well, if this has a volume of 800 centimeters cubed and it's water, that means it has a mass of 800 grams or 0.8 kilograms. Well, how did I get that? Well, I got that from this handy dandy density of water. It's 1 gram for each centimeter cubed. I got 800 centimeter cubes and each one of them has a mass of 1 gram. That's 800 grams. And so I know that this block of water is going to weigh 0.8 kilograms times G, which would be 8 newtons. And that means the buoyant force here would be 8 newtons. And that means the buoyant force on this block, since it's the same size and shape, would also be 8 newtons. Now you'll notice when it was floating, it only had a buoyant force of 6 newtons. Well, that's because 25% of that block was not displacing fluid. This part of the block that was pushing water out of the way was only 3/4 of the volume, or 600 centimeters cubed. And that's why I get a buoyant force of 6 newtons here, but 8 newtons there. Now, this yellow block is, if I draw a block of water that's the same size, it would have a volume of 400 centimeters cubed, and that means it would have a mass of 400 grams or 0.4 kilograms. Well, that block of water is going to weigh 4 newtons. And so the buoyant force on the yellow object would be 4 newtons. So that's part B. Part C is asking us to find the acceleration of each of these objects if they were set down on the surface of the lake and then released. Well, the green object's floating. It's just sitting there. It's not going anywhere. So if I put C over here, the acceleration of the green object is going to be 0. It's floating. But for the acceleration of the yellow object, I'm going to have to use Newton's second law. And before I do that, I'm going to draw a free body diagram for that yellow object. I got a weight force here that's equal to the mass times G. Well, that's going to be 0.6 kilograms times 10 newtons for each kilogram, or 6 newtons. We just said that the buoyant force on this yellow object when it's fully submerged was 4 newtons. Well, if I use Newton's second law, F net equals ma, my net force here, if I've got 6 newtons down and 4 newtons up, that's going to be a net of 2 newtons down, and that's going to equal the mass. The mass of that is going to be 0.6 kilograms times the acceleration. And that's going to give me an acceleration of, if I divide 2 by 0.6, I'm going to get 3.33 meters per second squared down. Okay, and that was arguably the most challenging part of that problem right there. Now the last part of the problem is we make a crown out of the same material as the yellow object. It's supposed to look like gold. When the crown is placed gently into a full bucket of water, 360 centimeters of water spills out. What's the mass of the crown? Well, we found the density of the yellow material is 1.5 grams per cc. So if I use that information, this is a simple plug and chug problem. The density of the yellow material is the mass divided by the volume. If this is 1.5 grams per centimeter cubed, and we want to find the mass if its volume is 360 centimeters cubed. Well, that mass is just going to be 1.5 grams for each centimeter cubed, and I've got 360 of them, and that's going to give me a mass of 540 grams, okay, for the crown. Okay, well, that has been problem 13. Let's erase the board and go to problem 17. Okay, so problem 17 has a table, and this time we have two objects. One is blue. Tell you what, I've got blue marker and I got a red marker, so let's do this blue object and a red object. Okay, and what we find is that if we have two beakers of liquid, and one of those beakers is going to be filled with water, and one is going to be filled with liquid Z. I'm going to do that in a different color than red. Okay. Liquid Z. Okay. And I know that the density of water is 1 gram per centimeter cubed, but the density of Z I'm not given. But I am told that the blue object, if this is H2O and this is liquid Z, the blue object floats in water, but it sinks in liquid Z. And the red object sinks, oops, do this in red, it sinks in both. Now we're also told that that the two objects have the same, that the volume of the blue object is equal to the volume of the red object. But they have obviously different masses because they have different behavior in water. Okay? Now the first question we're asked here is, what, if anything, can you say about the density of liquid Z? Well, I can say that the density of liquid Z has to be less than the density of water. Well, how do I say that? Well, I look at the blue object. The fact that the blue object floats in water means that the density of the blue object is less than the density of water. But the blue object sinks in liquid Z, and that tells me that the density of the blue object is greater than the density of liquid Z. And so now we can see that if I compare these two, the density of water has to be greater than the density of liquid Z, and that means the density of liquid Z is less than that of water. Okay, easy peasy, no problem. Now we carefully place the blue object into the beaker of water, and it floats. And what we find is that we get a puddle of 25 centimeters cubed of water. We put that same blue object in the liquid Z, and what we find is a puddle of liquid Z that has a volume of 30 centimeters cubed. Well, that tells me right away, in part B, we want to find the mass, the volume, and the density. So the mass of the blue, the volume of the blue, and the density of the blue. Okay? Well, I know that when something sinks and is fully submerged, where it is now, liquid used to be. And if it started out with this beaker full to the brim, displaced means it has to spill out of the beaker. And so this volume of spilled liquid is exactly the same as the volume of the block. And so that gives us one answer. I also know that when something floats, we talked about this in the last homework set, there's only two forces on it. There's the weight down and the buoyant force up. Well, this is equal to the mass of the object, the blue object, times G, and this is equal to the mass of the liquid, in this case displaced, times G. And if it's floating, there's no acceleration, so that means the mass of that object is the same as the mass of the liquid displaced, which in this case means spilled. And I know that because this is water, 25 centimeters cubed has a mass of 25 grams. It's 1 for 1. And so that means the mass of the blue object is 25 grams. The density now is just 25 grams, the mass of the blue object, divided by 30 centimeters cubed. That's the volume of the blue object. And this gives me 0.83 grams per centimeter cubed. Okay, now we've got two questions that are very, very important. And when these were put on an exam, these are exam questions that we're working through here. When this was put on an exam, it caused a lot of difficulty. So let's think carefully about this. Part C asked us to compare the buoyant force on the, listen carefully, the red object in the water to the buoyant force on the blue object in the water. Now, what's the same here? The buoyant force on the blue object in the water versus the buoyant force on the red object in the water. Both objects are in the water, okay? And they both have the same size, okay? Both of them are displacing the same fluid, water. But the blue object is up here with only part of its volume submerged, okay? It's floating, and so part of it is above the surface. Whereas the red object is completely submerged. All of its volume is pushing water out of the way. And so that means that the buoyant force on the red object is going to be bigger than the buoyant force on the blue object. So for part C, we say F buoyant, got to put a Y in there, on the red is greater than F buoyant on the blue. Because it's displacing more water. The red is displacing more water. Now, part D is asking us to compare the buoyant force on D, on the blue object, in water to the buoyant force on the blue object in Z. So now we're comparing this buoyant force on the blue object in water to this buoyant force on the blue object in Z. And here's where people fell off the bus. Here's where people had trouble on that exam. They said, oh, well, when it sinks, it's displacing its whole volume. Whereas here, it's only displacing part of its volume. So that means that the buoyant force is going to be bigger when it's completely submerged. Apples and oranges. You gotta think about what's the same here. Here, what's the same is it's the blue object and it's the blue object. The liquids are different. So even though it's displacing a bigger volume of liquid Z, it's not the volume that matters, it's the weight of the fluid displaced. And we've got a different density for liquid Z than we do of water. So we can't just say, oh, it's displacing more cc's, so it has a bigger buoyant force. That doesn't work. What we can use is a free body diagram. In both cases, it's going to be block B. And in both cases, the weight of block B is going to be the same. Just going to be the mass of the blue object times G. But when it floats, the buoyant force is big enough to support that weight, whatever it is. But when it sinks, that buoyant force is too small to support the weight, and it accelerates to the bottom of the beaker. And so I know that in this case, the buoyant force is equal to the weight. In this case, the buoyant force is less than the weight. So that means the buoyant force in water is going to be greater than the buoyant force in liquid Z. Okay? That's problem 17. Now, problem 18 is a really, really good exam question. It would be the sort of question you might expect on your exam. Okay, problem 18. We have this beaker and it's filled with water, okay? Now, you can imagine that we could do this same problem in a beaker filled with heavy cream and it would be even more exciting, okay? We have 2 blocks. We have block A and we have block B. Now, we're told that the mass of block A is equal to the mass of block B is equal to 500 grams, which is 0.5 kilograms. But we're told that the volume of block B is 200 centimeters cubed. And we're also told that block A is floating such that 3/4 is below the surface and 1/4 is above the surface. Okay, that's everything we know so far. Now, again, this is in water, where the density of the water is 1 gram per centimeter cubed. So part A asked, what's the buoyant force on block B? Well, that's going to be equal to the weight of the water displaced. Okay? Well, that's going to equal the mass of the water displaced times G. Well, how much water is being displaced by B? Let's imagine a block of water the same size and shape as B. Well, I know that the volume of B is 200 centimeters cubed. If I had a block that was also 200 centimeters cubed, how many grams would that be? Well, water has this nice relationship where it's 1 for 1, so that's going to be 200 grams. So the mass of the liquid displaced, the water displaced, is going to be 200 grams. But if I'm going to multiply that by G, I can't put in 200 grams. I've got to put that in as 0.2 kilograms, okay? 200 grams is 0.2 kilograms because there's 1,000 grams in a kilo, okay? Okay, and then I multiply that by 10 newtons for each kilogram and I get 2 newtons. So the buoyant force on B is 2 newtons. The second part asks us to find the tension in the string. Okay, and it doesn't matter whether I find the tension at the bottom end or the top end. It's a massless string. It's got the same tension at both ends. So let's draw a free body diagram for block B. Well, I have a weight force And I know that the weight force on that is just going to be a 1/2 kilogram times G, or 5 newtons. I also have a tension force up by the string on B, and I have a buoyant force up that we found was 2 newtons. And I also know that B is just sitting there. It's suspended by the string. And so if this diagram is going to scream 0, that means that, well, let me do it formally here. Let's say F net is equal to MA. Let's call up the negative y direction and down the positive y direction. So I've got a weight force of 5 newtons, that's down, so it's positive. I have a buoyant force of 2 newtons up, so it's negative. I have this tension force up, so it's negative, and that's equal to the mass times the acceleration, but the acceleration is 0, so that's going to give me 0. And if I solve for that, the tension has to be 3 newtons. Well, you knew that. I mean, I got 5 down, I got to have 5 up. There's 2 of it, that's got to be the other 3. So if I just use Newton's second law, I get the answer that screams to me anyway, that I've got a tension of 3 newtons in that string. Now, part C of this problem asks us to find the buoyant force on A. Well, again, we're talking about a buoyant force, that's a force. So let's draw a free body diagram for A. Well, I have a weight force, and again, both of these blocks have the same mass of 1/2 kilogram, so that's going to be 5 newtons. I also have a tension and a buoyant force on A, but now the tension force is down, not up. And we know that it's 3 newtons. And we know that the buoyant force is the only upward force. And this has to scream 0 again. So that means that the buoyant force on A has to equal the tension in the string plus the weight of A, which is going to be 3 newtons plus 5 newtons, which is 8 newtons. Okay? Now that black marker is not doing what I hoped it would. So the next part asks us a challenging question. Oh, that's just not acceptable. Oh, we missed it. Okay. It's asking us for the volume of A. Well, I know that this part of block A, we'll call that the volume submerged, is equal to 800 centimeters cubed. Well, how did you get that, Greg? Well, I know that the buoyant force on A is 8 newtons. Well, that buoyant force is equal to the weight of the fluid displaced by A, the part of the water that's pushed out by the submerged part of block A. Well, that buoyant force is equal to 8 newtons. How much water weighs 8 newtons? Well, I know that the weight is equal to the mass times G. So if this is 8 newtons, and G is 10 newtons for each kilogram, this must be 0.8 kilograms. Well, 0.8 kilograms is the same as 800 grams, and 800 grams has a volume, when I'm dealing with water, 1 gram for each centimeter cubed, it's going to give me 800 centimeters cubed. So this part down here is 800 centimeters cubed. But that's only 3/4 of the volume of A. So I can write that the volume submerged, 800 centimeters cubed, is 3/4 of the volume of A. And that means that the volume of A is going to be, let's get rid of the 3/4, we'll say it's 4/3 times 800 centimeters cubed, and that's going to give me 1,067 centimeters cubed. Okay. Now we're almost done here. We have one more step to go, and no, we got 2 more steps. This problem goes on and on and on and on and on. So let me get myself some room over here. Okay, so they're asking us now, if we had a block made of the same material as A, but had a mass of 800 grams. So, man, is this all the way up to part E? Will this problem never end? Okay, so the mass is 800 G. The density is the density of A. Well, I don't know the density of A, or do I? There's 2 ways I can go about this. One is I can say the density of A is equal to the mass of A divided by its volume, which is 0.75 grams per cc. No, that's not true. Oh, that's not true. Okay. That's going to give me 0.47 grams per centimeter cubed. And I said there were 2 ways to find that, but there's not. There's only one way. I was thinking wrong. I forgot that I had this anchor hanging it down. Okay, so that's the density. And I know that the density of A is going to equal the mass of anything made of A divided by the volume of anything made of A. And that means that the volume is going to be the mass divided by the density. That's going to be 800 grams divided by 0.47 gram per centimeter cubed, and that's going to give me 1,700 centimeter cubed. Okay, now, part F. I can see why my co-author didn't want to put this one in the book. If the string were suddenly cut, what would be the acceleration of that block B right after you cut the string? Well, I've got a free body diagram for block B right here. That used to be correct when I had the string there, but if I cut the string so it's no longer pulling, I take away this tension force here. And now I just have a buoyant force of 2 newtons up and a weight force of 5 newtons down. And so if I use Newton's second law, well, 5 newtons down and 2 newtons up is a net of 3 newtons down. And I've got a mass of 1/2 kilogram. That's given in the problem. And so that gives me an acceleration of 3 divided by 1/2, or 6 meters per second squared down. Okay, that was a good example of what you might expect on an exam, and to make it more sexy, we could fill that beaker with something like heavy cream or alcohol, something that had a density other than 1. And that wouldn't make it that hard. I mean, if you had heavy cream, where the density of the heavy cream was 1.5, well then, if this had a volume of 200 centimeters cubed, it wouldn't have a mass of 200, that would be for water where it's 1 for 1. Well, if it's 1.5 grams for every centimeter cubed, I'm going to have 300 grams here. And the buoyant force would be 3 newtons, not 2 newtons. And then the tension in the string would just be 2 newtons. It'd make the problem seem completely different, but it really wouldn't be that different. Think about that. Okay, I'm going to stop this recording.